Okay, you've probably heard that computers use binary numbers. What it means that these binary numbers use only two digits, 0 and 1. Despite this incredible simplicity, 0 and 1 can represent numerical values just as good as decimal numbers. So right here we have a traditional row of numbers 0, 1, 2, 3, 4, 5 and so forth. And if you want to replace these decimal numbers by the corresponding binary numbers, 0 would appear as a 0, 1 will appear as a 1, and 2 will appear as binary 10. Then 3 becomes 11 and 4. So with progression of these decimal numbers, if we want to rewrite them as binary numbers, you see that because we have only two digits, they really quickly grow in size. So they really kind of keep growing in how big this number is going to look like with only zeros and ones. So the internal use of binary numbers forces computers to manipulate types of data that have sizes like, and you can see that these are powers of 2. So we have the data that typically is a multiple of 2 or divisible by 2, whichever way you want to look at them. So for instance, our integer right here is 32 bits in size. You can have a bigger integer normally written as long, kind of strange data type right here, but this would most likely create an integer number which is a 64-bit size. So like I told you, these numbers are powers of 2. So for instance, 64 is 2 multiplied 6 times. So it's 2 raised to the 6th power. So 2 raised to the 7th power would be 128, and so forth. So the binary value of 64 is this, right? So this is like 1 with 6 zeros. So this is the binary number 64. So you see how quickly the decimal numbers, when they're converted to binary format, how quickly they grow in size. So this one requires 7 digits to be written. Okay. And when you look at even larger numbers, such as, for example, decimal 1, 2, 3, 4, 5, 6, 123,456, internally it'll be stored as this binary number. So this is very difficult to distinguish from another number which is close to this one, and generally we say that binary numbers are very unfriendly to us humans. Of course, a natural choice would be to use a decimal number, which we use conventionally in our math. But unfortunately, number 10 is really not a power of 2. Remember on the previous slide we said that inside computer, when we create our variables, their sizes are always multiples of 2. So for instance, a character is 8-bit size. An integer, as we had the original x written right here, an integer x is 32-bit, and so forth. So here base 10 or decimal system is not very effective in describing the sizes and other properties of variables that we store in computers due to their nature of using binary system internally. So I'll skip the octal numbers for a second and just go straight to hexadecimal numbers and talk about these. So these are decimal numbers, 0, 1, 2, 3, 10, 11, 12, and so forth. And hexadecimal numbers use hexadecimal digits. You can see that hexadecimal digits correspond to digits 0 through 9, but hexadecimal, which stands for base 16 system, needs 16 digits. So in decimal system we have 10 digits, 0 through 9. In hexadecimal version we need 16 digits. So the missing digits that simply don't exist in decimal system, we compensate for them by using letters A, B, C, D, E, F to make up. And so therefore this line here, these numbers correspond directly to 0 through 9. They are exactly as the decimal equivalents, but hexadecimal A is a decimal 10, B is 11, and so forth. F is decimal 15. So decimal 15 in hexadecimal notation is written as digit F. So if we want to continue this row to say, okay, what is 16? 16 will become hexadecimal 10, and then 11, and so forth. And you can see that these letters and conventional digits that we use in decimal system become mixed, and the numbers look like 2C and 2F and all sorts of combinations of all of these 16 digits that include A, B, C, D, E, F as well. This slide I will explain in our next video. Just for a second, I'd like to quickly jump to the missed part of this slide. Also mention octal numbers. Besides hexadecimal numbers, we also have an octal numbers, and these octal numbers are 0 through 7. So decimal 8 is written as 10. In octal system, which is base 8 system, there are only 8 digits and they stop at 7, and so octal 10 is decimal 8. I'm not going to spend too much time with this, but just to clarify what this octal number system means. And sometimes it's also used primarily when you start programming hardware devices. Oftentimes you need to manipulate 3 binary digits, and octal numbers happen to be the most convenient way to use them when you're trying to program hardware such as hard disk microcontroller and other types of hardware on the system. So in summary, hexadecimal numbers like these and like these over here are chosen to indicate memory locations. They're just much friendlier than binary numbers like this. So just to show you one more time an example of it, I'm just getting rid of duplication here. I will rebuild this program and run it one more time, and once again this is yet another address displayed on your screen. So here we create an integer variable which is allocated in memory. It belongs to function main. It's a local variable inside function main. It has memory address, and if we'd like to display the memory address, we use ampersand operator, which is address of X will be understood by character output device as us trying to display memory address, and naturally it converts this address to this hexadecimal number is made up of all of these digits. This slide, this hexadecimal notation, we're going to discuss in our next video.